we've learned derivatives in two directions. In the x direction, letting y be fixed and run the x direction, fix x and run the y direction. But now we're going to need derivatives in any direction. I want to know the growth, the rate of growth in any direction in the plane. So here is what's going to happen is that, let me sketch it here. We have a point, xy, x naught, y naught, and we have a graph of a function, so we have some function f of xy, okay? And what we know to do now is what happens if I go in that direction or if I go in that direction. What is the growth? What's the tangent line? What's the slope of the tangent line at the graph in those two directions? In this direction, I'm letting the y coordinate, y naught, be fixed, and I'm running x. So the slope in that direction was given by the derivative with respect to x. In this direction, I'm letting x naught be fixed, and I'm running the y coordinate. So this is at y naught. If I take the derivative and evaluate at x naught, y naught, I get the slopes of the tangent lines at exactly those points in exactly those directions, okay? But now, the new thing is that I want to go in any direction. So what happens if I go in that direction? How is going to be the rate of change in that direction, okay? So that's what we're going to do. Why? Because, for example, if you're on Horsebarn Hill, which is, let's see, it's like right here seems to be the highest point. And if you're going to sled down, then you want to try to figure out like where is going to be the steepest descent, all right? So if I want to, if you actually look at the topographical map, can I do this? Yes. If you look at it, then you can see that this area is sort of at the same height, while if I go all the way down here, that looks pretty low, but this looks even lower. So going in that direction seems to be steeper, and I want to know if I should go this way, that way. It just seems I want to go exactly in that direction, okay? So if I have a graph, if I have an actual function, a topographical function of every height, I want to know in what direction there will be the steepest negative slope, the largest negative slope, which will give me the steepest descent. Right now, I can only figure out what's happening in that direction and what happens in this direction, okay? So we want to do better than that. So here are the definitions we had, the limit definition for the derivative with respect to x, the limit definition with respect to y, and you see that we fixed y naught and we let x run, or we fixed x naught and we let y run. So to do it in a direction, and by the way, this is very important, that it has to be a unit vector. Okay, it has to be a unit vector. If I have a unit vector, then what I'm going to do is run values in that line that is with respect to that direction of a unit vector, in the direction of that unit vector. And to do that, when I move the x and the y exactly at this pace, they are coming to the point x naught, y naught in the direction of that unit vector. How do we actually do that? It turns out that once you know the main two directions, you can come up with any of the directions. It turns out there's a theorem that if the function is differentiable, so it means that it has derivatives, it has these partial derivatives, then the directional derivative in the direction of, again, I'm going to circle that because it's important that we use unit vectors when we do this calculation. The partial or the directional derivative in the direction of the unit vector u is given by this formula. So it's the partial with respect to x times a plus the partial with respect to y times b. Okay? More formulas to remember, not quite much, because this is the dot product, if you remember the dot product, which we should review at some point because it's part of the exam, if I take the derivative with respect to x, evaluated at x naught, y naught, comma, derivative with respect to y, evaluated at x naught, y naught, that is the vector with the partial derivatives, and I do the dot product with the vector, with the unit vector, that unit vector of coordinates a, b, this is exactly what I get. So it's the dot product of two vectors gives me the partial derivative that I want in that direction u. Okay? So let's see an example of this. I want to do the directional derivative in the direction of u. The direction is 1 minus 1. But again, sometimes these directions, they're just giving you a direction, but I need a unit vector in that direction. So the very first step here is to take my vector, 1 minus 1, and make it of length 1. So I'm going to divide this vector by its own length to make it of length 1. This vector has length, the square root of 1 squared plus minus 1 squared. So it is of length a square root of 2. So a unit vector in that direction will be the scale of my original vector by a square root of 2. So it will be 1 over the square root of 2, comma, minus 1 over the square root of 2. That is the vector that I want. That is a unit vector, length 1, and in the direction, in the same direction as the original vector u. Okay? And now I just need to follow the formula, find the partial derivatives, evaluate at the point, and then do the dot product. Okay? So let's take partial derivatives. What's the derivative of f with respect to x? I heard 3x squared. I'm using the power rule there. And minus 3y, because the y is a constant, so it's some constant times x. And the constant is 3y. And then if I evaluate that at the point 1, 2, I can just do that, and it's going to be 3 minus 6, which is minus 3. Okay? Now I take the derivative with respect to y. With respect to y, I'm going to get minus 3x plus 8y. Right? Let's take this derivative with respect to y this time. I get this. Evaluate at 1, 2, and now I get minus 3 plus 16, that's 13. Okay? And finally, I can take, let's remember this, 3 and 13. Okay, so let me all write it here so it's not all cramped. So the direction vector was 1 the square root of 2 minus 1 the square root of 2. The partial at 1, 2 was minus 3. The partial with respect to y at 1, 2 was 13. So now the directional derivative of f will be the derivative with respect to x evaluated at the point, so minus 3 times the coordinate a, so the first coordinate, so 1 over the square root of 2, plus 13 times minus 1 over the square root of 2. So that is 3 over the square root of 2 and 13 over the square root of 2, 16 over the square root of 2 with a negative sign. So that is the tangent line at that point in the direction of 1 minus 1 has slope minus 16 or the square root of 2. U1, yes. So U1 came here. I knew they gave me one vector, and I need a unit vector in that direction. So a unit vector in the same direction is given by, so unit vector u divided by its own length. Okay? That's why I calculated the length of the vector they gave me, which is a square root of 2, and then divided the vector itself by a square root of 2, so by its own length, to get those coordinates, but both divided by the same constant, which is the length of the original vector, a square root of 2. Good question. So I had to do that because in the definition of directional derivative, the very definition is given by a unit vector. So this formula works for a vector that is of length 1, because it just has to tell me in what direction. If I use a longer vector, it's going to tell me something different, like what is the growth in some much larger distance or something like that. If you go to this formula that gives me in the theorem tells me that I can compute directional derivatives using a vector as long as that vector is also a unit vector. It has to be of length 1. Divide by its own length, so it's in the same direction but of length 1. Let me give you another example. So now I want to find a directional derivative in the direction given by the angle pi over 6 measured clockwise from the x-axis of the function, this function. So first of all, what is the direction we want? So it's going to be a vector of length 1, and the angle here has to be pi over 6. So what are the coordinates of this vector? So remember that the points that are 1 from the origin are the points in the unit circle, and the coordinates of the unit circle are parameterized by cosine of the angle, sine of the angle. Since the sine of pi over 6 is a half, the vector that I want is cosine of pi over 6, which is the square root of 3 over 2, comma, the sine of pi over 6, which is 1 over 2. Okay? This was in clockwise. What did I say, clockwise? I'm going counterclockwise. I saw somebody moving their hands. If I do this, it's counterclockwise. So if I want to measure it pi over 6 clockwise, I should move in that direction pi over 6. So this is going to be, instead of the y coordinate being a half, it's going to be minus 1/2. Okay? So that is because it is clockwise. Okay, so now I can take derivatives. Let's find the partials with respect to x. What is the derivative of ln x squared plus y squared with respect to x?
2x over x squared plus y.
Yes, 2x, the derivative of the inside divided by the inside, because the derivative of ln of x is 1 over x. So this is x squared plus y squared. Okay? And then evaluate at 1, 0. That's the point where I'm going to look for a directional derivative. Evaluating at 1, 0, the denominator is just 1, the numerator is 2. So this is 2 divided by 1, so it is 2. The derivative with respect to y will be very similar. 2y x squared plus y squared. And if I evaluate at 1, 0, because the y is 0, I get 0. Then the directional derivative will be the directional derivative of f, in this case, will be the derivative with respect to x, 2 times the square root of 2 over 2, plus the derivative with respect to y, 0, times minus 1/2. So that is 2 times the square root of 2 divided, or square root of 3 divided by 2, which is a square root of 3. Okay. So that, as I said when I was defining the directional derivative, I can reinterpret it as a dot product of this vector, the vector of partial derivatives, this vector, dot with the unit vector that I want a derivative in that direction, right? So then the formula for the directional derivative is just given by a dot product. So that vector itself has a name. It's the gradient vector. So this symbol itself, we just say gradient of f, and it is that vector. So we can find the directional derivatives on using that formula instead. Let's use it with this directional vector. Again, the direction of u is fine, but u itself is of length not 1. The length here is 3 squared plus 4 squared. That's 9 plus 16 is 25. The square root of 25 is 5. It's of length 5. So I'm going to divide by 5 to get a unitary vector. So I want the directional derivative in the direction of 3/5 I plus 4/5 j. OK? And then just find the derivatives. So the derivative with respect to x, that is 2x y cubed minus cosine of y. Evaluate at 1, 0. The first term here, y is 0, so that goes to 0. The cosine of 0 is 1. Again, because I think you should know what are the cosine, sine cosine values of 0, 30, 60, 90, 45. So cosine of 0 is 1 if you look at the unit circle, what the x-coordinate is. So this is just minus 1. The derivative with respect to y is, so it's going to be x squared, 3 times x squared, y squared. And with respect to y, I'm going to get plus x sine y. Evaluated at 1, 0, I'm going to get y is 0, and the sine of 0 is also 0, so this whole thing is 0. So the directional derivative of f will be the the gradient vector evaluated at 1, 0, dot product with the vector 3/5, 4/5, which is, I calculated the directional, the gradient vector to be minus 1, 0 at that point, dot product with 3/5, 4/5. That gives me minus 3/5 plus 0 times 4/5, so it's just minus 3/5. So that is a directional derivative in a direction using the formula in terms of a dot product. All right, let's maximize the directional derivative. Now, when we were looking at that topographical map of stores, we want to find sometimes we want to look all around us and find what is the steepest ascent and what is the steepest descent in a graph. Or if you have some function that represents some economic factor, we want to know how should we change our values so that we have the highest increase in value, or what is going to be the worst case scenario, how fast can our value decrease. So to maximize the directional derivative, let's see what would be the largest we can make this be. So suppose I have fixed a point, x naught, y naught, right? And I want to know in all directions from that point what is the highest value or the smallest value of this function. So I want to know how big that value can be. But that value is given by a dot product evaluated at the point dot with this directional vector. And we know we have a formula for the value, for the length, or for the value of a dot product. We have a formula that is the length of the vectors, the product of the length of the vectors times the cosine of the angle between them. Okay? So now, can I simplify this? Yes, because this piece here is a unitary vector. So that is just 1, right? So this is, in fact, just the length of this times the cosine of the angle. But now this is evaluated at the point. So the point is fixed, so this is fixed. And what changes is this factor, cosine theta. So I want to make the cosine theta as big as possible, but the cosine theta can be between -1 and 1. So what will be the largest possible value is when the cosine is 1, which is when theta is 0. What does that mean? What that means is that the largest value of this will happen when the angle between the gradient and my unit vector is 0. So when they are parallel. So we want the gradient to be parallel to u for the maximum value. Okay? So we want those two to be parallel. So now we have a way to figure out, given a function at a point, where will be the largest possible value of all the possible rates of change in every direction. It will be given by the direction that is parallel to the gradient vector. So this is what this theorem says, that we will have the largest value when u has the same direction as the gradient vector, and the largest possible value is the length of the gradient vector. So let's see that in an example. Find the directional derivative in the direction of u, and also find the maximal directional derivative of the function. So let's just find one value first, and then compare to the actual max. So again, this vector 1, 1 is not unitary, so I'm going to change it by this divided by its length, which is the square root of 2. So let's compute the directional derivative in that direction. The directional derivative will be, let me compute partials. The partial of f with respect to x will be 2x ln y. Evaluated at 3, 1, ln of 1 is 0, so this is just 0. The partial with respect to y will be x squared divided by y, because the derivative of ln y is 1 over y. Evaluated at 3, 1, that is 9. Okay? So when I do in this direction, it will be the dot product of 0, 9 with the direction 1 over the square root of 2, 1 over the square root of 2. And that is 9 over the square root of 2. So that is one of the possibilities, is that we go in that direction, and the slope is 9 over the square root of 2. Now I'm going to find the maximal rate of change. The maximal directional derivative will be given by, if I go in the direction of the gradient vector. Okay, so this is just duf in the direction of 1 to the square root of 2, 1 over the square root of 2. So let's see what happens if I compute the maximal one. The maximal one will happen will be in the direction of delta f, or the gradient f, that is not a delta, gradient f at 3, 1, which we saw it was 0, 9. That vector is not of unit length, but the unit length vector in that direction will be 0, 1. Okay, so now I want to see what happens in that direction. In that direction, the derivative will be the gradient vector dot that direction, which in this case is 9. So this is the largest directional derivative is 9 versus previously we computed that in some other direction it was 9 over the square root of 2, which is a bit less than 9. So if you want to go fast, you have to go in the direction of 0, 1, moving in the y-axis. Why did I use 0, 1? So I have to use a directional derivative in the direction of 0, 9. But 0, 9 is not of unit length. So I'm changing it by a vector of unit length. So if you compute the length of this vector is 9. So I changed it by 0 divided by 9, 9 divided by 9, which is 0, 1. Okay? Divide by its own length to get a vector in the same direction of unit length. You can see that 0, 9 is a vector that is going in the y-axis, but it's very long. So I know that now it's in the y-axis, so just pick the basis vector 0, 1 instead. Okay? Now, some properties of the gradient vector that are going to be very useful. So it turns out we can look at the gradient vector in a new way. Suppose I have a surface, which is the graph of the function z equals f. Then I can bring the z to the other side of this equation to make it 0 equals. Okay, so from here, I can write it as 0 equals f of xy minus z. And now think of that as a cross-section for a function of 3 variables. So think of this function, which is this function. And then I can do a level surface at t equals 0 to get this surface. So this is a level surface for this function of 3 variables. But we know that the normal vector at a surface like this, if I want to find the tangent plane, the normal vector, we figured out what the formula was. The partial derivatives, the vector of partial derivatives with respect to x, with respect to y, with respect to z of this function gave me the tangent, gave me the normal vector to the tangent plane. So this vector, which is the gradient vector for this other function, is actually normal to the surface at any point. So it turns out that this vector, in the graph, this vector is normal to the surface at any point. And similarly, this vector is normal to any of the level curves at any point, indicating the maximum rate of change. So let me repeat that, but with a graph here. So suppose I have some graph like this. Okay. So at any point in here, if I want to figure out what the normal vector is, my normal vectors are usually in red. That normal vector to the graph at that point is given by the partial with respect to x, partial with respect to y, minus 1. That vector actually gives me a normal vector to the surface at that point. And if I cut it, and I actually look at a cross-section, so my cross-section now looks like this. If I go to the corresponding point here, and I want a normal vector to that place, a normal vector, so a vector is perpendicular to the tangent line, it turns out it is given by the gradient vector. Okay? And that indicates that in terms of level surfaces, it's telling me that in that direction, there is the steepest descent, okay, or the steepest increase. There is the direction where there is I think, in fact, in this case, the vector would be pointing in the opposite direction, just so to indicate that actually the growth would go in that direction. So I think the delta is actually going in the opposite direction in this case. But let me just redraw it. So in this case, it would give me a vector that is perpendicular to the tangent plane, but it's actually pointing in that direction, so that this point, this one goes like this, telling me that if I want to increase the fastest, I should actually go in this direction, which indicates that I should be going in this direction to the tippity top of the paraboloid. Okay? All right. So, yeah. So this is going to be important properties of the gradient vector that we're going to use in what we call Lagrange multipliers. This property of where these gradient vector points will be used in the topic of Lagrange multipliers to solve other more complicated problems about rates of change with constraints.